Good morning and welcome. My name is Jo Adigbola. 3 years ago at this event, we announced AWS Batch to the world. It's been a wild and wacky 3 years, and a lot of the development in the service today has been driven by diversification in workloads that you are bringing to AWS Batch. Today we're going to update you on where we are at with Batch and some new releases, and then we're really proud to have Matt from Uber ATG here talk to us about how they are using AWS Batch for autonomous vehicle simulation. So as with AWS Batch, AWS itself is seeing a huge diversification of workloads. And this is really driving us to innovate and provide additional features and services and categories of workloads, support for categories of workloads that you can use to place your workloads in the cloud. We've added additional capabilities with improved and increased speeds on Intel's chips. And we've added accelerated computing and enhanced networking offerings to also help with additional workloads. With over 270 different instance types today, the ability to bring new workloads and meet new business needs is greater than ever. But as the diversification increases, we continue to invest in this space, and we will continue to do so because we expect that trend to continue. So I don't know about all of you. While choice is awesome, sometimes it can be a little bit overwhelming. And when we originally launched AWS Batch, we did so because customers were telling us that in some cases, they were plugging together 20+ different AWS services in order to launch a batch workload. That's a lot of undifferentiated heavy lifting for results in your batch workload. So batch as a service, and as it was when we launched and as it is today, is a set of batch primitives that are going to not only allow you to schedule and place workloads onto instances, but it's also going to handle the scaling up selection and scaling down of instances on your behalf. It's going to help you remove that undifferentiated heavy lifting of getting your workflow running in the first place. So because it's a native AWS service, you are going to, from your own code bases, have full access to the suite of AWS services from within your codes. This gives you a great deal of flexibility and openness. Batch is going to provision those resources on your behalf based on business rules that you provide to us, the specifications of the jobs that you may have. And it's also going to allow you to take advantages of things like Spot, should you feel that that's the best thing for your business. So looking at who's using Batch today, we're going to hear about the use case of autonomous vehicles from Matt in just a second. But we have many different areas and segments that are using AWS Batch. So one example would be Western Digital, who uses AWS Batch today to simulate energy-assisted recording technology. AWS Batch allows them to easily shrink the simulation time down from 20 days to just 8 hours, dramatically improving the time to results. Matterport uses AWS Batch to process thousands of 3D models for their customers on a daily basis, tens of thousands even. And they bring down the creation time for their containerized application environment from more than a year to just a few months. And then in the life sciences space, Cubic uses AWS Batch to analyze genomics data. For example, gene expression differences between deceased and normal tissues. And the automation and orchestration provided by AWS Batch potentially cuts their research by 50%. So these are all really great examples of Batch. If you're interested in learning more about them, they are available on AWS on our case portal. So please feel free to go read about them. But the big trend is you all continue to surprise us with new and innovative ways of using AWS Batch. This really drives our roadmap, and we really encourage you to reach out and let us know what you're doing, because that helps us really continue to develop the service and make it the best thing that we can make for you. So let's look at a typical batch architecture. In this case, it's image transformation. The very first component that you're going to think about when setting up a batch job is to use the job definition. This job definition is really the nuts and bolts. It's your application image itself, any configuration, any data that you may need, and any permissions that you may want to use for accessing services within batch or even external to batch. So in this case, with an image, this image may be submitted manually. It may come down from a satellite feed and drop into an S3 bucket. Once in that S3 bucket, you can configure a Lambda function to automatically process this image as it comes in and place it into the batch queue. Once jobs are submitted to the batch queue, they're going to sit there until there are resources available for them to run. The scheduler is going to be constantly evaluating the job definition of each of those jobs in the job queue to see what kinds of instances are going to be appropriate to run those instances on, the availability of those instances within the compute environment, and also just how many there are so that it knows how many instances you may need. It's going to be looking at things like vCPU, the GPU requirements, and obviously the number of them for each case. So once they're in the queue, they're going to run in approximately the order in which they arrive. As we'll talk about a little bit later, jobs can have job dependencies. So assuming all jobs prior have met their dependencies, the in order is mostly there. And you can obviously choose which instances you would want those to run on. So if we move them across, the scheduler is assessing that job queue. It's found enough jobs that make sense to spin up an instance or multiple instances. The compute environment is another measure for you to really say what is right for your business. Do you want a warming pool of sorts with a minimum number of vCPUs available, so you always have some available, so it's very quick to get going? Do you want a maximum vCPU where you're going to cap how many instances you would have running? Those types of things are available to you to set up. You may want to be very specific about what instance type you want to run on, or just specify an instance family. And if that is all too much and you don't want to do that at all, Batch's intelligent scheduler can use the job definition file to choose on your behalf, in which case you would choose the type optimal. So once the instances are all available and spun up, Batch is going to place those onto those instance types on your behalf. It's going to pack them intelligently onto the right instances so they're as efficient as possible. And one of the other benefits is the complexities of where those are going to be placed is done for you. So you can have jobs of many different types in the job queue at once. And this batch scheduler is really going to choose where is the best place to put those jobs at any one time, according to the parameters you set. So those jobs are going to execute, they're going to run, and when they complete, we receive a job return code. That return code to the scheduler informs the scheduler that now there's a slot for the next job to move. It's going to reassess what's in the job queue, and it will continue that process until there's no jobs of that type left or no jobs at all, and then it will start to spin down the instances that are no longer used or needed on your behalf. So with that, I'm going to hand over now to Steve, who's going to walk you through some of the latest releases on AWS Batch. Thank you, Steve.
Thanks, Joe. How's the sound? Can you hear me okay? All right, awesome. I'm Steve Kendricks. I am the Senior Technical Product Manager for AWS Batch. I'm going to walk you through a little bit of how, so Joe kind of talked you through, hey, here are the key components of Batch, here's what our customers are doing. I want to kind of bring out some of the new innovations we brought to Batch recently in the past year. I'm also going to talk a little bit about the machine learning use case for AWS Batch and how that applies to what Matt will talk about with the Uber Advanced Technologies Group use case. Right? One thing that Joe talked about is the ability for Batch to scale up instances on your behalf. Right? The idea here is that AWS Batch will manage your scale for you, right? Based on your workflow requirements, you shouldn't have to think about the instances, right? And we're continually getting better at doing that. One of the key things that we've done about a month and a half ago is to launch what we're calling allocation strategies, right? Batch originally had a single behavior when launching instances, and we called it essentially a best fit allocation strategy. What best fit means is that we would launch the least number of instances on your behalf, right, to run the jobs in your queue. And what that means, right, and that's valuable for a few reasons. The first is so that we can increase your utilization, right? If we can have a single instance where we can pack a lot of jobs onto it, right, that reduces spin up and spin down time, we can then continue and increase throughput as well, right, and reduce cost by including as many jobs as possible on a single instances and keep replacing those instances, right? We do want to give you the least number of instances. And this was really good for most customers, right? Batch would do a cost optimization. It would give you essentially we would do our own calculation. We would turn a list and we say, great, let's give the customer the instance that is going to charge them the least for their workloads. However, some customers came to us, especially customers like Matt, and said, well, that's awesome, but one thing that we like to use is Spot. And one thing that what this behavior does is it will pick a single instance type and it will sit there and it'll say, I know I need this instance type. I'm going to wait for that capacity because I don't want to charge the customer anymore. What customers like Matt did is push us to kind of expand what Batch can do and think about, right? And make cost and throughput trade-off decisions. Right, so we launched 2 new allocation strategies that let customers scale out a little bit more reliably when using AWS Batch, especially in the spot market, right? So we launched Spot Capacity Optimized, which if you are familiar with Spot's Capacity Optimized allocation strategy, it's very similar to that, right? AWS Batch will receive the inputs. Either you will say, hey, Batch just give me the optimal mix of instances, right? You figure out what Batch should launch, or if you have specific instance requirements, you can tell Batch, I only want these particular instances, and Batch will sort through those. It will still say, great, I want to launch these instances for the customer. However, when using Spot Capacity Optimized, Batch will take a look at the spot market, right? We're going to take a look at the spot market. We'll communicate with our underlying services in AWS. We'll say, here are the mix of instances where we can find the deepest capacity pool in Spot, right? What that lets you do is say, if I need, maybe I like to run on C5 18XLs, I also can run on M5 24XLs or a C4, right? What that lets you do is it really lets you diversify. And so if I say, well, great, this mix of C4 and this mix of C5 and M is really what's going to provide the customer the deepest capacity, right? That gets you the benefit overall of reducing the amount of spot reclaims that you're going to experience, right? And so what that means is, of course, overall, as you're trying to scale out, it lets you experience much higher growth, right? So customers before, right, were able to reliably launch 100,000 vCPUs, right? Now we can start looking at millions of vCPUs because we can now reach across multiple and many different instance families. Right? We also release, and that's great in the spot market, and we do recommend that any customer using Batch with Spot use Spot Capacity Optimized. We also launched for on-demand, right? We also launched a similar feature called Best Fit Progressive, right? I already explained how Best Fit worked, right? It launched the least number of instances, right? That can fit the jobs in your queue in most cases, right? With Best Fit Progressive, what we do is we still create that list and say, listen, let's get the lowest cost or the best fit instance for your workload. However, in the case, maybe even in the case of a spot reclaim, right? If I know that I want that M424 or M5 24x large, but I can still run on M5 12x large, right? Batch is going to launch that M5 24x large. We think it's the best. If there's a capacity limitation, for example, we will then start launching those additional instance types and progressively sort through the list for you. The best thing about this is you don't have to think about any of it. All you need to do is essentially say, here's the instances I want to run, or even Batch figure it out for me, and here's how I want to run. I want to maximize my spot capacity. Batch will handle everything else for you. How we tie this together, right? Joe introduced the concept of submitting jobs, right? So let's say a user here has a job that is submitted to their appropriate queue, right? I then have 2 compute environments, right? This is a very common use case. right? You obviously aren't restricted to this. I'm just showing you one example, but this example says, right, listen, maybe I'm running maybe a financial risk analytics firm. I need to have, and I say I need a certain level of throughput, right? I know I need a certain level of throughput that I want to achieve. I want that in on-demand, right? So I have 100 jobs that take one vCPU each. I'm gonna restrict this top compute environment, this on-demand compute environment, to where I think that level of throughput is. So I'm going to launch 100 jobs, 100 vCPUs worth of jobs into that compute environment. I'm going to cap that on-demand compute environment at 100 vCPUs. I'll use a best fit progressive allocation strategy. And then after that, I can spill over into the spot market, and every additional instance that spins up, right? If my users come in and it's over 100, right, where I expect that kind of low level of throughput that I really need to make sure my business is running, comes through, and users say, no, we're going to submit 400, or I'm going to submit 10,000 jobs today, right? The rest of those jobs is then gravy. I can save 70, 80% in the spot market, right? And Batch will manage that for me. And because right after that, all I really care about is that capacity, I'm going to use spot capacity optimized strategy, right? So let's talk about, right, so I talked about some of the things. I have a few more kind of newer releases to talk about. But I want to tie it and bring some of these things together. How does this fit together for machine learning and for simulations? Right, one of the things very often that we see customers need, especially in the machine learning workload, or machine learning workloads, is the need to express workflows, the need to have dependencies, the need to build pipelines, right? And AWS Batch is a great fit for the batch scheduler component of that workspace, right? What AWS Batch allows you to do is kind of express dependencies based on workflow need and not have to manage instances, right? So if, for example, let's assume that I submit all of these jobs at the same time to AWS Batch. I have a setup job, I have a heavy network I/O step, I have GPU intensive step, I have a memory intensive step, and then after that I have some analysis and some cleanup to do. What Batch will let you do is submit all of this at the same time. I express dependencies on the jobs on each other, right? So the setup job comes in, Batch says, great, I'm going to spin up an instance, I'm going to run this job. I'm going to hold all these other jobs, right? I'm going to hold job B, C, D, E, and F in pending, right? When job A is finished, Batch is automatically going to move job B, right? The array job, if you're familiar with the concept of array jobs, Batch will move array job B into runnable. We're going to launch instances appropriate to that job requirements, right? vCPU memory requirements, right? And the good thing here is as job B is running, it has an end-to-end dependency, or I should say job C has an end-to-end dependency on job B, right? So as B0 finishes, job C starts, right? We're going to spin up an instance, a GPU instance for job C, right? Or C0, right? And if B99 finishes first, we can launch C99, right? And so the whole thing is you only get the instances, you get those compute instances for the workload type that you need when you need them, right? You don't need to pay for example, memory intensive steps while you're sitting there waiting. Batch will spin up the memory intensive when it's time for the memory intensive jobs to run, and only when it's time for them to run. You don't have to worry about having memory intensive instances sitting there being unutilized while your heavy network and I/O step is running, right? And after that, we can submit some jobs. We already have those jobs submitted in the queue, and after that, they just automatically run when the dependencies are finished, right? One thing that we launched last year is multi-node parallel jobs, right? This is another way for Batch to manage your instances. A multi-node parallel job is important for those tightly coupled workloads. If you think distributed deep learning, or you think MPI, right? This is something that you'd be familiar with. An MMP job is a single job spread across multiple instances, or as we call them in this case, a node. Right, a node, and as you add nodes, right, it's important to keep adding and having a tightly coupled network with low latency, right? Because as you add nodes, of course, the communication needs to be between all of the nodes in the cluster. Batch will manage this for you, right? We'll spin these up. When you submit your multi-node parallel job, Batch is going to spin up instances, right? All or nothing, right? And when you have these clusters, right, you say, I need 100 instances, or I need 100 nodes, all at the same time. I need 1,000 nodes, all at the same time. I need 32 nodes, all at the same time. But what I can't use is I can't use 31, right? That doesn't do me any good. I need all 32. When Batch spins up a multi-node parallel job, we make sure we spin them all up at the same time for you. And if there's a capacity limitation, we make sure you're not charged for that intervening time, right? But also what we don't do is we don't spin up 10, and then we spin up the 20, and then we spin up 31, and then we spin up 32. We spin up all 32, right? And that's there to save you money. We also are integrated with the Elastic Fabric Adapter, which is essentially a custom-built low latency interconnect between instances. Again, as we said, as we add nodes to this network, right, the latency then begins to build up, and it's important to have a low-level interconnect between the nodes to make sure that latency is reduced. Right. GPU scheduling. We launched GPU scheduling earlier this year, and what that allows you to do is express your jobs in the terms of the GPUs that it requires. Right. So we accept P and G family instances, but essentially you say, I need to have, right, my job requires 3 GPUs or 4 GPUs. We will spin up an instance that has 4 GPUs on it. We will place the job on the instance and pin the GPUs against the container to make sure to prevent oversubscription, right? So if you have maybe two GPU jobs running on the same host, right, there's no oversubscription of the GPU. Here's how you kind of tie that together, right, for deep neural network training, right? You have, for example, this is just an example instance using P3DNs. But in for example, you have your multi-node TensorFlow container application. We will then spin up the P3DNs for you. We'll spin up in a placement group, right? A placement group is essentially an AWS artifact to make sure that your instances are located physically close together, right? That reduces latency. And then underneath, you can use a high-performance file system such as FSX for Lustre, which, right, is critical for kind of communicating, in this case, back and forth between the nodes and the file system, right? And it takes care of reading and hydrating back and forth between S3. On the right, you see kind of the performance that you can get with AWS Batch. Remember, I talked about kind of latency spikes as you add nodes in the cluster. What you really want to see is a nice linear scaling of compute, right, of performance as you add, in this case, as you add GPUs. You don't want to see kind of performance begin to tail off as you add them, right, as performance demands improve, right? And what you like to see is this nice linear scaling graph. So we have a lot of customers that build, because of the tools that Batch provides, we have a lot of customers that build workflow managers on AWS Batch, right? Luigi, Airflow, are kind of what we would consider more general purpose or machine learning specific applications, right? Nextflow is a very popular healthcare and life sciences workflow manager, right? That is built and very popular with AWS Batch. Lyft, just a few weeks ago, released their Flight machine learning platform that is hosted on Kubernetes, but it essentially uses, or in very large part can use AWS Batch. And just yesterday, Netflix announced their Metaflow machine learning workflow. This is our workflow manager. This is the workflow manager that they use in-house. They just announced yesterday that they will open source Metaflow using AWS Batch in large part to scale out applications, right? So you see kind of this growth of machine learning-based workflow managers, and many of them are utilizing AWS Batch because of these tools. So I've talked a lot about machine learning. I've talked a lot about simulations, how Batch works. But one of the best things about the job that we have here is the ability to have customers stretch us and push us in interesting ways. They have extremely interesting insights into how Batch works, into how our services work, and they are awesome, the most awesome provider of feedback that we can give. And I'm very pleased to introduce to you Matt Ranney. He's the senior staff engineer at Uber Advanced Technologies Group to discuss his use case and what he's doing with Batch.
Thanks. All right, thanks. Can you guys hear me? Great. Okay, cool. So I want to talk to you about what I do, which is self-driving cars. And so we're going to take a little detour from AWS Batch. We'll get back there. But to understand like what we're doing with Batch, I want to explain to you a little bit about like how self-driving car development works. So first off, we take this car. This is our vehicle platform. It's a Volvo XC90, and it's a little bit Volvo makes it a little special for us, so we can add a bunch of this extra stuff on. We use the Volvo automatic emergency braking system, but then we add a bunch of additional sensors, like we had radar, and then we had cameras, and then we had LiDAR on the top. That's the thing you see spinning around. More cameras, and then in the back is a pretty hefty compute stack, which has got about 5 computers back there that sort of process all of the sensor data and figure out how to drive the car. And so all of that, so we have all of these, like this giant pile of sensors, and it's producing a ton of data. And all this data has got to goes into some software. So these are the major software modules that make up our system. Other stacks may be a little bit different, but this is, there's usually something like this in most self-driving stacks. And the amount of software here is tremendous. This represents the work of hundreds of engineers who've been working on this for years. It is a very complicated, very large software project. And the output of that, of course, goes to drive the car, like make it move through the world. And so what I want to talk to you in general about, like what we use Batch for, is how we test this system. So there's a compute stack that kind of runs all this stuff, but it's a lot of software and it is complicated. And so on board, we have some data that we sort of package up the software. So when you make a new software release, you package it up into this read-only section, which has got a sort of secure boot firmware, signed operating system, signed binaries. But we also include a bunch of trained models and some HD maps. HD maps are this sort of high-resolution version of the place where we want to operate the vehicles that gives us very precise localization and other sort of traffic, information, or sort of how to act on the road. And there's also a writable area where we log all the sensor data. So whenever the vehicles are driving around, they're always logging all of their sensor data. Just always, keeps getting written to that writable area. We got some, diagnostics and telemetry as well. But right, so how do you test all of this software? It is a lot and it is complicated. Now, obviously, we do the normal stuff that you would do to test software, as you would write unit tests, and we use modern Clang. The autonomy software is all written in C++, and so there are a lot of great tools around there to sort of help the individual modules sort of be more robust. And of course, we can stick these things together, in some ways to make some integration tests. But the really tricky part is, if you look at this stack, there's a feedback cycle there. When the software says drive a little bit in some way, that changes the input to the software. And also the real world is kind of moving around, and so it is very hard to test this software in isolation. It's very, of course we want to do subsystem testing, but really the only way to understand whether the software is doing the right thing is to test it end to end as a whole system. So to help with that, we built this track. So this is a facility near our office in Pittsburgh, Pennsylvania. This is on the site of an old steel mill. We've got a whole road network here. It's all mapped out. The roads are all named after Mr. Rogers' neighborhood because Mr. Rogers was from Pittsburgh. So that's pretty cool. But on this track, we can recreate all of the driving scenarios that we want to test against, things that we will encounter in the real world. And we can do so repeatably and safely because it's a closed course. And so we have a lot of other actors we can bring into the scene. Like we have this little robot guy that can move around, and then we have little robot doors that can open, and so there's a bicycle version of all this, and so we can test this stuff. We can actually test the software end to end. That's the real software running on a real vehicle in the real world. And so we have a team of test engineers that set up these tests. They have their laser triggers, and they have different roamers, the robots, the human or bicycle stand-ins. We call those roamers. we've got ambulances and school buses and city buses and police cars, and we can recreate all of these scenarios on this closed course. And we use this methodology of scenario-based testing. So like there's a specific capability we're trying to exercise, and so the team specs out like, oh, here's how we want the scenario to work. This is where the interaction happens. This is these are all this sort of the geometry of how we want a scenario to be executed. But as you can imagine, this is not, while a very accurate and realistic way to test the software, it doesn't have very high throughput. It takes a lot of time. So these tests run at real time on real vehicles, and there are a lot of scenarios that you want to test for every new software change. And then, as big as that track is, like there's only so many cars we can fit on it at a time. And so, but importantly, like every developer really wants to test their software individually. Like if it takes a day worth of track testing to validate your software, like that's pretty bad throughput, right? You would like it if every change that you wanted to land, you could validate something, validate the performance independently. So then, you don't have to group your changes together with everybody else's. So that's where we turn to simulation. So simulation is running the software on something that isn't the vehicle. And so there are a couple, two major types of simulation that we do. The one on the top is called hardware in the loop, and that's where we use real vehicle hardware. Either we take the compute stack and we just put it on a test bench, or maybe we take a few of them and we stick them in a rack in a data center, or at night when the vehicles are docked, we can actually use the real vehicle hardware, just reroute the sensor inputs, and sort of use these very powerful but unfortunately expensive compute stacks to run the real software. And so this is hardware in the loop testing is great in that it tests all the sort of integration points, so you can make sure that all the software will work on the actual vehicle hardware. It also is really good for testing how the performance, the actual performance on the real hardware, whether the tasks are interfering with each other, whether we're getting the latency that we need, etc. But unfortunately, it does not scale very well because you have to have actual vehicle hardware, at least the compute stack built up somewhere. So that's why we turn to software in the loop testing. Software in the loop is not the same as the vehicle hardware. We use commodity hardware, and we also do something, we also run the software differently in that we want to get deterministic results. So when you're validating a change in the software, it's very hard to work with the randomness of the real world, and you would like to get repeatable results. So to get repeatable results on real hardware is very hard. But with software in the loop, we orchestrate the order of execution, and so we can make sure that for a given set of inputs, it will always generate the same outputs. But as a side effect, it means that it runs much slower than real time. So software in the loop runs much slower than real time, but good news is we can run thousands of them at the same time. So there are a couple types of software in the loop simulation that we run. One is log-based simulation. We call it log sim. So remember, when the vehicles are driving around, they're logging all their sensor data. So anywhere it goes, all of that sensor data is saved. And when we bring them into the depots, we offload all these logs. If something interesting happened in one of those scenarios, we can replay that sensor data through a new version of the software. And so this is the sort of flow through the software stack. Like the sensor data plays through all those components I showed before. But then there's a vehicle model, which is a physics simulator that says, okay, based on these controls, like here's where the vehicle actually moved. And then the pose is the position and orientation of the vehicle. So we send that back, and then the loop starts over. A log-based simulation is interesting in that it very accurately represents what happened in the real world because it's actual sensor data. So it's replaying the same thing that really happened. There are a number of downsides, though, the biggest of which is the logged actors, all of the other actors in a given scene, they only do what they did when the log was created. So if the simulated, if the simulation decides to do something a little bit different than what the original log did, actors might just walk right through us, or run in the back of us, do various impossible things because they're not, they're on rails. So to fix that, we have another type of software simulation called virtual simulation, which is where we use a game engine to make a virtual world and move the actors around. And then we don't quite have all of the sensor data, the fidelity of the sensor data, but we still run the rest of the stack. And we still have this feedback cycle, but at this point it is a truly closed loop simulation, because if the simulated AV does something different, the actors can react to this new behavior. The big thing with virtual sim is, because we control the world, because we have a game engine that can move actors around in the world, we can parameterize the actor motions and do lots of variations of the same kind of interaction. So here is just sort of zooming in on a few of those. But we can say let's make the pedestrian come out a little bit faster, a little bit slower. Let's change our approach speed. All these kinds of things that you can explore if you can parameterize the space. And what we find is, in order to be useful, we need to run thousands of these simulations to explore a parameter space, which is why we're here. So this is an example of the output that we get from running a big parameter sweep. So in this simulation, we're varying 3 different things. So there are 3 dimensions of variability in the scenario, and then we can sort of explore the vehicle's performance, and you can sort of slice and dice based on what's happening. And this is, just to give you a sense, each one of those dots represents 10 individual jobs that are individual array job elements. And so these are large batch jobs. So here's an example of how we use these large jobs to make the software better, to sort of tighten the loop of writing the software. This is an intersection in Pittsburgh where we want to drive. And so right there you see a stop sign. This is what we call an unprotected right turn. So we want to be able to turn right there, but there's no stop sign for the vehicles coming from the left. So we want to drive there, and we haven't driven there yet. And so we want to make sure that if we do drive there, that the software will do the right thing. So we recreated this intersection in the simulation, and then we did parameter sweeps of oncoming traffic, and we only swept in 2 dimensions. But we found an interesting thing, which is this should have been super easy, because these are not challenging scenarios. But if you look at that little red square there, we found in a couple of cases it didn't actually do the right thing. And so it sort of looks like this, which is we're hanging out, we're thinking maybe we should yield to that thing, and then due to a bug, so that's unfortunate. But we never would have found that if it wasn't for simulation, if it wasn't for large-scale simulation with parameter sweeps. It would take forever to recreate those exact conditions on the track or in the real world. But with simulation, we can just run another one of these things and just make sure we fixed it. So here's another motivating example. This is a really tricky problem where a pedestrian runs on a red light against a bus, and you can't see through the bus. She can't see us. We can't see her. It's a pretty tricky problem. And so in order to make sure that we can always handle this problem, we recreated it at the track, of course. And we can do variations at the track, so we have laser triggers, and there's code you can write for these things, and so we can sort of do crude parameter sweeps at the track, of course, in real time, and make sure that we think we handle it on the order of tens of variations, but to really make sure that we handle it, we have to create this scenario in our virtual world. And so this is an example of the editor tool, and so the person can add a bus, and then you can put the AV in there, and then start adding actors, and sweep parameters around, and it is really just absolutely essential to be able to do these simulations and large parameter sweeps to validate the software. Okay, so that's why we're doing simulation, is to test our autonomy software, and we're doing it in AWS using Batch, obviously. And this is an ideal workload for this type of thing because the demand is not predictable. Jobs are launched when engineers have new software they want to test. So a new, maybe that lines up with the working hours of the day. It tends to be people don't land too much software at night or on the weekends or holidays, but it is also unpredictable because you don't know who's going to land, want to test what changes whenever. So a very, very irregular demand, and the sizes of these tests are, they vary wildly, and they represent what would be equivalently, thousands of real vehicles, an impractical scale to do in the real world. Because some of these tests are 100,000, and we're not there yet. But our engineers are asking us to be able to run 1 million. So like 1 million, Batch can't do this, and neither can our simulation infrastructure. But this is where we want to get. This is some of these problems require really, really large explorations of the parameter space. This is just a quick graph of our compute environments that Batch feeds into. You can see, like, on the weekend, that's that low point on the right. People are still running some stuff. Some people are working on the weekends. But then come Monday morning, it cranks right back up again. And, that's how that works. So we have, I'm going to take you through some of the infrastructure pieces, some of the pieces we've built to work with Batch. And the first thing that we've done is we made a thing that we call deployments, which are implemented with some CloudFormation and a little bit of tooling that we wrote. And the idea is that every developer should have their own environment in which to work. So if you want to make some changes, you should be able to do so without impacting anybody else. So every engineer can have their own testing environment where they can play around without worry about breaking anything. But we've also got sort of staging and production environments. What you get out of each deployment is a sort of namespaced version of, or in some cases, an entirely separate version of. You get 2 Auroras, apparently, due to a typo. But yeah, so it's a way of just allowing developers to make changes safely without stepping on each other. But also, and this has been my favorite part, is it's also how we deploy the software. Is each deployment is wired up to the load balancer, and so when we roll out software, what we'll do is first we'll make a new deployment of it, and we will have this staged up and ready to go. And when we want to release it, we flip the load balancer to just point at the new deployment, and if we want to roll back, we can just flip it back. And this has worked out really well for us. So we wrote a lot of software around Batch to kind of make all of this stuff work. And I'll take you through some of the pieces here. There's a web UI, which is the sort of the user interface that the engineers look at. There's also the API. The UI uses that, but there are some command line tools that talk directly to the UI. Or to the API, sorry. The web UI is in Fargate. The API server is also in Fargate. We use Aurora for a database, and when we launch each job, each simulation, there's kind of this top-level concept we call an evaluation, which is like a group of a bunch of simulations. Each evaluation gets this thing called the tracker, which is kind of a meta batch. So I'll get into that more in a little bit. Inside of the container, we've got a few other components. Finally, is a system under test down there. That's the actual autonomy software. And inside the container is also this sim engine. We have a bunch of different compute environments. So just in prod, like LogSim and VirtualSim use different instance types. They have different resource requirements, and so we use different compute environments for that. We try to do all of the work on Spot if we can get capacity. Hopefully the new allocation strategies will help us more reliably get that capacity. We're excited about that. We also are doing a little bit of work with GPU instances. Some experiments that people are working with use GPUs directly. And so Batch lets us schedule some of that. So you might wonder, like, why did we have to build all this software? Like, there are a lot of yellow boxes up there, and like, isn't that what Batch is here to do to begin with? Well, there are some reasons for that. The first is our containers are very large. If you recall, the onboard components, we've got some operating system and these binaries, we got models, we got maps. All of that stuff needs to be available when we run the simulation, because like that's what the autonomy software uses. And so we make a container, the simulation container, that has all of that stuff in it, but unfortunately it ends up being about 8 gigabytes. So when you want to run 10,000 of those 8 gigabyte containers, this takes a long time. It's pretty expensive. A big reason for that pain is Docker write amplification. And if you're not familiar with that, this is the problem where every Docker pull operation does effectively write your data twice. So first you have to pull the layer, and it goes somewhere on your instance. Like maybe it goes out to to a file system on EBS, or maybe you have a local instance storage. But then when you extract it, you have to write the real version out again somewhere else. And for us, the best option we can come up with for that somewhere else is TempFS, which, if you're not familiar with it, is a file system in memory. And it's the only thing that we could get the reasonable performance out of these large images with this write amplification. And we amortized that cost of having to spend memory on this by using the largest instances that we can. So M5 24XLs and or whatever the largest ones that we can get. And so that way there's only one. It minimizes the amount of TempFS overhead that we had to pay for. So the other problem that we have is there are limits in Batch. At the moment, you can only run 10,000. A array job is maximum size of 10,000. And we need to run hundreds of thousands. So to work around that, that's where this tracker comes in. So what tracker does is it has a separate queue, and it will launch possibly multiple batch jobs like enough to sort of execute the overall evaluation that we're working on. And the way that works, I'll show you that in a second. So we launched multiple batch jobs. Another problem is the task with these very large jobs. Sometimes our tasks don't always run run for the same duration. So sometimes they might take 10 minutes, sometimes they might take 20 minutes, or sometimes they might take 2. And sometimes they might exit early due to, I don't know, bugs, or they're just like failing, or it's a bad software change. Remember, the point of running these simulations is to validate the software, and it may be that the software is bad. And if the software is bad, it might just crash right away or something. And unfortunately, what that does to Batch is make a tremendous number of AWS API calls very, very quickly, and blows through all of our rate limits. So to work around both job size, task length, and the container size, we built this tracker abstraction, which uses Batch to effectively spin up workers. And the workers come up and they go to the tracker and they say, "Tracker, what should I do next?" And for a given evaluation, the container is fixed. It has the system under test the software we're trying to evaluate. And all of those containers are spread across possibly multiple batch jobs, and they all sort of drain the queue out of trackers as quickly as possible. So the other problem is it's pretty hard to tell what Batch is doing, unfortunately. It's getting better, but especially when you start running multiple jobs spread across multiple batch jobs, it's really hard to tell what's going on. And I would say this is the place where we have spent the most time, is just trying to understand like what's going on here, because we produce a lot of artifacts. Some of those are for observability, and some of them are a necessary byproduct of what the simulation does. So every simulation produces another log and a bunch of other things. Like we make a video of what happened in it, and there's a bunch of metrics that come out of there. all of the components are all logging things, and there are some sort of lifecycle events that we use. We use Kinesis to tell Tracker how things are going, and so we have like a stuck detector in there, and some other things that so Tracker can kind of manage the overall life cycle of this simulation. But we had to, so we take all of these things and we build a UI out of it. So this is what the UI looks like, the user-facing UI. So someone launched this evaluation, and they'll see something like that, and you can drill into all of those scenarios and see the videos and the details. But what I want to talk about is the observability. This is the sort of the admin UI that we built, and so we built this timeline which shows, like, for that evaluation that we were just looking at, like when all the jobs ran, how long they ran for, and so you can see like they're not all the same length of runtime, and it's that sort of timeline view has been really essential to figuring out what's going on. So the way that we did all this is we made sure that every component in our system logs as JSON, and if it doesn't, we convert it. And this even includes the AWS SDK that doesn't by default log, at least in the Golang one, doesn't by default log as JSON, and we changed it so that it does. And this works really well with CloudWatch, but it also lets you use all the other tools in the JSON ecosystem. And so this is an example of kind of the old style of human readable logging that is probably familiar to most people. It's like a message that a developer left for another developer that a human might interpret. So the sort of structured version of it, we would write out something like that. So it's easy to kind of aggregate and process later. But then we add in a bunch of extra context. So for all of the events that get logged in our system, we have roughly that, roughly all those things in there. So you can tell, you can figure out what's going on. You can make a UI like that, or just drill into different problems. And so, for example, if everything is logging as JSON, you can use CloudWatch to figure out across the entire system, across all of your runs, all of your batch jobs, how often, this is a graph of how often things got retried. And so you can see we had a little spike there for some reason that I hope someone figured out. But anyway, so wrapping up here, there have been some problems. We've talked about the Docker thing, the ephemeral storage on ephemeral compute. So not a lot of great answers there. It's really tricky in batch if you're and in Linux in general. If you are running low on memory, if you're right up against your memory limits, you often don't get killed. So we had to make ourselves an pre-killer to work around that. And unfortunately, the AWS Batch is not that friendly for end users. Like if you look at the console, like it's sort of hard to figure out what's going on, and we just had to build some tooling around that. And I know I'm told the console is gonna get better, is getting better all the time. I totally believe that. But what I've definitely seen is the actual performance of Batch has definitely gotten way better since we started using it about a year ago until now. I forget the multiplier, but it is much faster than it was before, and it keeps getting faster. And in spite of all those problems, we still use Batch. And we still use Batch because it handles this scale better than anything else we tried. It's running 100,000 things is a hard problem, and not a lot of schedulers can handle that. And it also, I didn't talk about this too much, but our engineers often need to run some just ad hoc experiment on 1,000 things. Like they tried something once on their workstation and they want to just run it 1,000 times slightly differently. Maybe not even a simulation, maybe just something to work with some of their data, or try something out. So we let engineers run these batch jobs from their workstations, and they do this pretty regularly to just run ad hoc experiments. So another thing that big lesson that we learned is a lot of times people would write benchmarks and they would say, let's see how fast this goes, or let's see what the limits are here. And they would draw incorrect conclusions. They would say, oh no, it's way too slow, or it works this one way. And we have found again and again that any kind of benchmarks or testing or whatever that you might do, it's always best to validate those with the account team to make sure that you're testing it right or that you're drawing the correct conclusion. Sometimes our tests were correct, but often, very often, it turns out there was something that they could change, or if we would just do it a little bit differently, that things would be way better. Docker sizes, write application is a bummer. Add the preum killer. Sometimes tempfs is the best choice. It seems weird to store your Docker data in memory, but sometimes I think that is actually the right answer. Log for the machine, not for people. And that's all I have. And then I think Steve's coming back. All right.
Thanks, Matt. All right, awesome. So again, like I mentioned before Matt came up, one of the best parts of the job is a user who stretches us, who tells us, bluntly where we could improve, where we need to, essentially says, so I don't necessarily want to be building these things on top of Batch, or I don't necessarily want to, do certain things for you, right? And these are things that we as the Batch team are working on and are going to improve, right? So again, Matt talked a lot about the console and some of the observability features. We're gonna be investing some significant time next year into improving the Batch console, right, and making it a lot easier. We also are going to be integrating with Container Insights, which is a container level metric monitoring tool, right, which is going to provide job level metrics for you, right? Speed and scale, right? Matt mentioned that Batch has gotten a lot faster, right, since he began using it. Probably about 5-ish times faster than when he began, or a little bit more than that, than when he began using it, right? And we're always looking to improve the speed and scale, but also the reactivity, right? How fast does Batch react to jobs coming in, and how fast it can spin up the instances and spin them back down again in response to events. Also better placement logic, but essentially overall, right, any improvement that Batch makes is going to fall into the place of increased utilization, lower cost, and increasing scheduling fairness and dealing with multiple users and multiple workloads. All right, so that's all we have for you today. Thank you very much for coming. We're going to remain for questions afterwards, so if you would like to ask any questions, just feel free to come up. Thank you very much. Don't forget to fill out the session survey.